the sum of my individual energies times the number of particles per state. On average, I'm going to have, because I added up the total number of possibilities in this state divided by the number of states, which is 26. So times n sub I. So this is the number of particles per state. And this is the energy of that state. So and I want to make sure I'm not losing out on actually yeah, I'll hand wave through some of this. All right. So this means that I'm just adding up energy times, so therefore the change in total energy would be equal to the change in particles per state. So the energy was fixed. And so this would just be energy at some level, lost my subscript there, over n sub I over some other letter times delta F. So what I'm getting towards here is that we had very discrete levels right here. And so we did a sum. However, if we're dealing with some change in this F for very small quantities, we're practically doing integrals here. So this would translate mathematically as in the energy. And there's a per unit volume that I'm sort of hand waving over. So energy per volume. Integral of whatever the average energy is for some particular frequency. So this is the average energy for some particular frequency times dN dF. This right here is known as the density of states. So where does this connect us with anything else? If I know what the average energy is and I know the density of states, I can just integrate and I can figure out how much energy I have per unit volume. Energy per volume. And in classical physics, this is equal to the Boltzmann's constant times temperature. It is completely independent of frequency. The density of states here is equal to, and do not have that fraction memorized, is equal to 8 pi frequency squared over c cubed. So what we have here is, well, I'm going to pull constants out front. So this is equal to the integral of pull constants out front, kBt, 8 pi, c cubed, and I'm left with f squared df from 0 to some final frequency. Now I know calculus is not something that you're doing every day, but basic polynomial, what's the integral of f squared df?
2f df.
No, that's the
That's what?
That's the derivative. You went the other, we're going the other direction.
it's like something f cubed over 3.
Yeah. So basically, when you did the derivative, you multiplied by the coefficient and then subtracted 1.
Yeah.
When you do the integral, you do the opposite.
Yeah.
So you add 1 and then divide. Instead of multiplying and subtracting, you add and then divide. So this would be f cubed divided by 3.
Yeah.
So that when you do the derivative, you multiply by 3, they'll cancel out, subtract 1, go back to here. From 0 to whatever the final frequency is. So if I were looking at something coming off of an object, the total amount of energy coming off of it depends upon what that last frequency is. Well, there's no reason for that last frequency to be anything in particular. So this would give me an infinite amount of energy. Which means you light up a match, you look at the frequency of the light coming off of it, and if you look at the total energy coming off the small little flame there, it would be an infinite amount of energy. Or the sun, or anything that's emitting radiation. This in physics is known as ultraviolet catastrophe.
What?
Ultraviolet are the higher frequencies, and so basically, if you look at low frequencies, as long as this F doesn't get too big, this actually matches experimental data. However, once you start getting into ultraviolet or higher frequencies, what classical physics predicts is that you get an infinite amount of energy. Obviously, this is not what happens.
That'd be pretty scary if just lighting a match could,
Destroy all existence.
yes.
What experiments showed, if I look at the energy output, there's so many different ways of expressing this, but for frequency, we'll just do energy for frequency. You get this peak right here, and then it tapers off. What the classical physics predicts is that it matches pretty well for low frequencies, and then it just shoots up to infinity. There's obviously something wrong with classical physics. Enter Max Planck. Max Planck basically looked at this curve right here, and he thought, well, let's see if we can come up with an equation that works. And he did. Publishes a paper and says, in essence, I don't know why this works, but I don't know why this is the equation, but this is the equation. As in, he had no understanding about why that equation should be the one to describe it from a physics point of view. Mathematically, he knew it worked. And so then he spent the next couple of years trying to basically back justify it, trying to come up with some explanation. This is known as phenomenological physics, where you have the phenomenon and then you try to, in some sense, rationalize it and hope that you rationalize it correctly. The assumption he made was that the energy of the photon is proportional to the frequency. That's the assumption he made. Because there's classical physics, there's no relationship to frequency in the amount of energy. He makes that assumption and things fall into place. And that is what remains for Monday. No, Wednesday. It is Monday. That's what remains for Wednesday.